Hello, this is Wei Chengdu from Shandong University. In this video, I will briefly introduce our work titled TSTM Temporal Segmentation for Task-Relevant Mask in Visual Reinforcement Learning Generalization. This work studies how temporal information can help visual reinforcement learning agents focus on task-relevant regions and improve generalization under distracting visual changes. This presentation is organized into 4 parts. First, I will introduce the motivation. Then, I will present the overall TSTM framework and the temporal segmentation network. After that, I will explain the optimization objectives. Finally, I will show the experimental results. Let me start with the motivation. In visual reinforcement learning, many existing masking methods rely only on a single current observation. However, single frame masking is often unreliable. As shown in this example, when the agent and the background share similar colors, segmentation becomes difficult. Without temporal information, the predicted mask may include irrelevant background regions or miss important parts of the agent. Our key observation is that temporal cues from consecutive observations can help distinguish the agent from distracting visual content. Based on this idea, our goal is to learn more reliable task-relevant masks from observation sequences. This slide shows the overall framework of TSTM. Given an observation sequence, we first apply temporal segmentation to produce task-relevant masks. We also augment the observation sequence and obtain another mask sequence in the same way. Then, the masked observations are encoded into representations. On top of these masked representations, we introduce invariant learning and actor-critic optimization. More specifically, TSTM has 3 key components. The first is temporal segmentation, which extracts task-relevant masks from observation sequences. The second is invariant learning, which improves robustness across original and augmented observations. The third is policy consistency, which stabilizes policy learning under visual perturbations. So overall, the pipeline is observation sequence, temporal segmentations, and then invariant learning together with actor-critic optimization. Next, I will briefly introduce the temporal segmentation network. The network follows an encoder-temporal-decoder architecture. The encoder extracts spatial features from sequential observations. Then, a convel STM module captures temporal dependencies across frames. This is the key part that allows the model to use temporal information rather than relying on a single image. Finally, the decoder predicts task-relevant masks. The main takeaway of this slide is that temporal modeling improves segmentation reliability under visual ambiguity. This slide summarizes how TSTM is optimized. First, for teacher and student segmentation, we train a teacher segmentation network and distill it into a lightweight student model for efficient inference. The teacher is supervised with BCE loss and dice loss. Second, for invariant representation learning, we align the masked representations of the original unaugmented observation sequences. Here, the invariant loss is applied in representation space. It encourages the model to produce robust and consistent embeddings under visual perturbations. Third, for actor update with policy consistency, the actor is optimized with the standard DES-AC objective, plus an additional policy consistency term between the original unaugmented masked observations. So the key point is the invariant loss acts in representation space, while policy consistency is added to the actor objective. Now I will present the main experimental results. On the DMCGB benchmark, TSTM achieves the best average return among all compared methods. Under the video easy setting, TSTM reaches an average return of 935. Under the video hard setting, TSTM reaches an average return of 859. As shown in the table, TSTM consistently outperforms strong visual RL baselines on most tasks. The learning curves also show that TSTM achieves stronger final performance across both the video easy and video hard settings. Overall, these results demonstrate that temporal segmentation can significantly improve policy generalization in visually challenging environments. This slide further explains why TSTM works. On the left, the ablation results show that removing temporal segmentation causes the largest performance drop. This indicates that temporal segmentation is the most critical component of the framework. We also observe that invariant learning and policy consistency further improve robustness and overall performance. On the right, the visualization results provide a qualitative comparison. Compared with previous methods such as SGQN and MODI, our method produces cleaner masks with less background leakage and preserves the agent structure more accurately. These quantitative and qualitative results together confirm the effectiveness of TSTM. Thank you for watching this video. If you are interested in this work, please feel free to visit our poster during the conference session or check the project link on the slides. Thank you very much.